Hello. So thank you very much for having me. It's a pleasure to be back here in Berlin. As Tim just said, this is actually my second time on this stage. And it's a conference that, as everyone's already mentioned this morning, has a community that is dear to my heart. And so it's actually an honor to be able to be back here speaking again. So thank you, Chrissy, Polly, Kevin, and the rest of the team, and this awesome work that they've done, and especially for even allowing me to bring my child here. I've got a 1-year-old baby here with me called Freddie. Come and say hello to him afterwards. I'm trying to get him on the CSS party pack later on to do some obnoxious CSS animations as well. So we'll be kind of live coding over there with Freddie if you want to join in. So my name's Patrick Hamann. You can catch me on Twitter there. And I work at Fastly. We're an edge cloud provider that specializes in real-time content delivery. And my role there is a web performance engineer, where I spend a lot of time thinking about how we can improve the speed of our network, but most importantly, delivering content for our customers and their users as fast as possible. And so some of that I'm going to talk about today and show you some of the research that I've been doing. So why am I here? You're probably wondering what the title CSS and the first meaningful paint even means. And so hopefully all will come true shortly. So I want to ask you a question of how do you measure the performance of your website? What does being fast even mean? Is it how long it takes to get to a load event? Is it how many bytes you send down the wire or how many requests? But I would argue that it shouldn't be any of these things. Ultimately, we are building websites for our users or our customers' users, and it should be about how they perceive the speed of your website. Should we even have a golden performance metric? Does it even exist? I would argue that it shouldn't. And for years, we've been optimizing our pages to be built for these metrics that they directly correlate to how our websites are built, but not the user experience and how users are perceiving these things. So time to first byte, or document complete, load event, how many requests I sent. None of these correlate to a good user experience. And as I can't stress enough, at the end of the day, we are building our websites for real users, and they are coming here to do something. And so fortunately, we're seeing rise of a whole new collection of metrics focused around user experience, such as the speed index and the first meaningful paint, which we're going to talk about today, and time to interactivity. And we're also seeing rise to thinking about custom metrics specific to our needs. Maybe for a search results on a search page, it's how long it took the user to be able to find what they were looking for. Or a news organization, it's how long it took the user to find an article and read it. We should be thinking more about metrics specific to our users' needs and not focusing on how we delivered and built our technology. And so we're going to focus a bit on time to first meaningful paint today. So what does that even mean? To put it simply, the first meaningful paint is the time when a page's primary content appeared on the screen, i.e., to put it simply, the time when the thing that the user actually came to that website appeared on the screen. More detailed, it's the first paint after which the biggest above the fold, so we only care about the viewport. If you can imagine on a mobile screen, that's only what appeared in the first viewport has happened. And so layout is when the browser converts all of your elements and your CSS queries into an X and Y coordinate, i.e. where that element is going to be painted on the screen and its width and its height. So the browser has to perform layout of all of the elements in that above the fold viewport and paint them to the screen. And most importantly, TTFMP also takes into consideration when custom web fonts have loaded, because I've heard that we all like to add custom web fonts to our websites these days, much to my disgruntlement and disagreement. But maybe this is better represented visually. What does TTFMP actually mean? So TTFMP is actually a very new metric. We've only started using it since last year. Some folks at Google wrote an amazing white paper, I'll release these slides later, where they detailed how we can go about ascertaining the time to first meaningful paint. And unfortunately, it's not exposed via JavaScript API yet, though we are talking about it. And you have to be able to use for instance, Chrome's internal tracing to be able to do this. But on the top here, we have a graph that represents how many layout objects are actually painted to the screen. So that's time on the x-axis and the amount of objects on the y-axis, and how that correlates to the user experience below. And as you can see here, Google do something very clever, that they flush the head of their document way before they even send the search query back to the database. And so it paints very quickly on a 3G and emerging marketing network. You've got a paint at 1.5 seconds. But actually, the meaningful paint, the thing that the user actually came here for, is at 1.9. And we can see how that directly correlates to the amount of objects that are painted to the screen. And hopefully, you've now got a much better indication of this is a metric that's much more useful than start render or your time to first byte, because we've given the user what they came here for. And this is the type of metric that we should be focusing on and talking about and building and trying to optimize for. And maybe this is a better visually represented like this. So this is the ft.com homepage. And who here thinks the time to first meaningful paint is 3.5, 4, 4.5, 5? So yeah, the TTFMP here is actually 5 seconds on a 3G connection. So you're probably wondering how you can measure your TTFMP yourselves. Fortunately, Google have open sourced and built, you can contribute to this Lighthouse, which was, they actually built this tool as an auditing tool to audit how your new progressive, shiny web app was performing against some of the best practices. But it turns out that some of the audits in it are actually very good just for any website. You don't have to use service workers or progressive web apps to use Lighthouse to audit your tool. And using Lighthouse, you can install it via a browser plugin or a CLI and have it part of your build process. You can expose the TTFMP of your own website. So I urge you to go home and check this out and try it out on your own. So let's dive straight in of how we can optimize our own websites for that TTFMP metric and how this relates, and it's extremely tightly coupled to CSS. And obviously this is CSSconf, but it's unsurprising, hopefully to most of you, that CSS is so critical to how we deliver a good user experience to our users. And so we're going to look at past, present, and future best practices for how we deliver CSS and the assets that are related to it in the browser. And hopefully you'll be able to apply some of these methodologies at home. Now, to do this, it's very easy to create a test case study using a to-do MVC app. Sorry, Adi, if you're in the room, but it's much better, I find, to show use real websites to optimize for, because ultimately we are, again, all building real websites and not just to-do MVC app that delivers in 2 files, and we decide to throw a metric crap ton of JavaScript down the pipe at the same time. And this is, using real-world conditions is when we can really see how the optimizations have effect. So therefore, for the purpose of the talk and the research, I'm going to use the ft.com homepage, and we're going to apply some optimizations together to it to see how we can improve the time to first meaningful paint. So just a disclaimer here, I used to work for the Financial Times, so I chose it because I know how the page is built, and they've given me permission to do this. And in fact, I think some of the developers who still work there are in the room, and but you know, it is actually a very good, fast website, but we can probably improve it, and that's what we're going to try and do. And so for each optimization, we're going to be testing on a real device, and I can't stress this enough. And to do this, we're going to use webpage test. If you haven't used webpage test before, I urge you to go and do it. It is the #1 toolbox in my arsenal of tools, because it allows me, one, to test on real devices. There is a real Moto G sitting at the end of this form, and it allows me to shape to a real network condition that, again, we are building websites for real users, okay? Contrary to popular belief, the shiny iPhone that you have in your pocket is not a real-world device. And actually, the average device globally is a low to mid-end spec Android that has a very terrible CPU performance and very low memory. So webpage test allows us to actually test on these physical devices. For each test, we're going to run 9 tests and choose the median result of them. And we're going to use 3 network conditions, which I'll chat about later. My friend Ben is actually going to be talking about this kind of data of real-world devices and what is the real network at JSConf this weekend. So I urge you to go and look at his talk. So we need to ask ourselves these questions first, to be working out what our average user profile is. Where are your users based? What is their device landscape? In what context are they using your website? And I would be very surprised if one of you can tell me that you have a single context for your users, because that just doesn't exist. The same person might be accessing your website on a flaky mobile connection in the morning and then goes at lunchtime to use that same website on their fast iMac with their fast cable connection. There is not this single context. What is their network profile? And what specifically did they come here for? And that's what you should be optimizing for. So for the purpose of the test, we're going to be trying to deliver a first meaningful paint in 3 seconds on an emerging market network, which has a 400 millisecond round trip time. So that's the time it takes from a request to go from the client to the server and back again. 400 milliseconds just on an emerging market connection. And we're going to try and optimize for 1,000 milliseconds on cable. But I can't stress this enough, that you shouldn't be taking my baselines as what at home and what you should be using. You should be thinking about what your user profile is and setting budgets for those. And so that we can measure the impact of our tests and our optimizations, we need to set a baseline. And so this, hopefully, it will look very familiar to all of you. This is a HTML document that right near the top, we have a link element referencing our compiled main CSS file. I don't care how that was compiled or if it was authored in JS or whatever, as long as you're delivering your CSS like this, this is probably how we have been delivering CSS since the birth of cascading style sheets. And it's probably how most of you in the room are still delivering your CSS. So if we were to run that in webpage test, this is the waterfall result we got. And so hands up if you have seen network waterfalls before, use them on a daily basis. Awesome. So it doesn't matter if you haven't. So the x-axis here is time, and the y-axis is the network request that the browser is making, and the priority and the order in which that happened. Webpage test fortunately gives us MIME types here. So we've got HTML is blue, CSS is green, images are purple, JavaScript is orange, and fonts are red. And for each one of these segments, there's 2 shades of color when we sent the request, and then the waiting period, and then the download process, and how long it took. So here we can see that we requested our HTML file. It found the link element because it parsed the document incrementally. That's a great thing about HTML spec, is it can be parsed incrementally. It found the link element quite soon during the download of the HTML and triggered a request. And then the green line here is our start render. So that's not our time to first meaningful paint, but that's when we started painting on a 3G emerging market. So that gives us a baseline of around 8,000 milliseconds TTFMP on 3G and emerging market, and around 2,000 for cable. So way out of our budget. So now we've set a baseline. So the first experiment we want to do is we want to inline our critical CSS. And hopefully many of you have heard this technique. This is what I came to this very stage to talk about in 2014. And since then, it's become quite a common practice. So let's have a quick recap of that. The first we need to do is we have to look at our critical rendering path of our page. This is the single path that a browser must do to be all the steps it has to do before it can paint to a screen. So first we have to make the get HTTP request for our index file. We get the response for that. We can start building the document object model. This is the DOM that we all interact with in JavaScript, which is a tree-like structure representing the parent-child relationship. So I have a body tag inside that has a div, which has a p, which has a span. And we can construct the DOM as we parse the HTML incrementally. So we don't need to wait for all of the bytes of our HTML file to be downloaded before we can construct the DOM, which is an often overlooked but amazing feature of the HTML specification. We find the link element. We then have to go and stop constructing our DOM because our CSS is known as a render blocking resource. And we have to go and perform the networking for that, get that, and then we can construct our CSS object model, which is exactly the same as the DOM. But note the idle time here. We've wasted a lot of time on our network connection waiting for that CSS file. And also note the fact that, imagine if I was on a train, I was looking at Twitter, I clicked on a link to the FT, I downloaded the HTML, and then I go into a tunnel. And so I have no network, and now I don't have enough network to perform that CSS, but actually I've got all of the content. I could just paint to the screen. So what we've actually done here is we've created a single point of failure by delivering our CSS as a separate object. whereas we do have all of the information. So the theory here is, what if we were to inline the critical CSS just required to render that first viewport, the one that we care about for our first meaningful paint, into the head of our document, then declare the rest of it as asynchronous, telling the browser, I don't care about this for the first paint. And so now we have all of the information we need, probably within the first round trip of a network connection. So then we can construct the render tree and render to the page. So going back to our experiment, this is now what it looks like. We now have a style element in the head of our document. This goes against everything we've been taught about separation of concerns, of styles in our style sheets, behavior in our JavaScript. And then we're using our new friend, the link preload element, which we can talk about later. And here I'm using the filament group's load CSS function to do this. So I think this is, for me, the best way about doing this at the moment. And it's got a little polyfill for browsers that don't support this. So what if we were to run this in webpage test? So let's recap. This is our baseline. Remember where the start render line is there. And now, with inline, look, we've instantly got painting as soon as we've started to parse the HTML document. We no longer have to wait for our CSS because we've declared that as asynchronous. And so you can imagine this is going to have a very dramatic effect on our time to first meaningful paint metric. And so here you can see we now have a 63% improvement on our baseline. We've got 1,300 millisecond time to first meaningful paint on cable and 3,200. So we've basically halved it, which is extremely impressive just using one technique. But this comes with some pros and cons. We now no longer have that single point of failure. We've eliminated all of the blocking resources. But the eagle-eyed in the room would notice that probably because we've declared our other CSS as asynchronous, that still has to be loaded, and we still have to apply it to be able to paint to the DOM. So it causes a reflow. And that's why it's really, really important that you separate your truly critical everything in that first viewport from the non. Because if you were to have stuff that was in the top of the viewport inside your non-asynchronous stuff, you're going to cause reflow and actually have a jarring user experience. The most important point to note here, though, is we've made it not cacheable. By inlining our CSS into the document, every time we change that CSS, we're essentially invalidating the cache for all of our HTML files. So if you can imagine something like the ft.com, that's a very large cache that we're going to be invalidating every time we change some CSS. And we don't benefit from the browser caching that object, and then we're actually going to be sending more bytes down the wire every time, which is completely unnecessary. It's also very hard to maintain and very hard to automate inline CSS. I've worked on some very large-scale websites, and it's become a pain that there's no optimum way of doing this. So we've been able to get our CSS down as soon as possible, but how can we then prioritize the delivery of the other sub-resources that our CSS requires to achieve that time to first meaningful paint? I.e. the critical resources for our page. So I want to ask you a question of, can you think about what are the critical resources that you have on the website that you were building yesterday or today even for your customer or your company? Can you think about those right now, top of your head? The resources that, if the network failed, I only need these 1, 2, or 3 resources to be able to deliver a good user experience. The rest of them, the ads, code for the JavaScript, that can all be left behind. Have a think about that. So let's identify the resources together for the ft.com page. Is it the logo? Is it the custom web fonts? And we know that TTFMP has to use the custom web fonts, and actually we're delivering the news. The user needs to be able to read it. Or is it the hero image to give some context? And I'm very sorry here for the Theresa May photo bomb. I'm actually really annoyed with myself that I've included her in this deck. She doesn't deserve it. So how can we go about automating the process of choosing these critical resources? Fortunately, again, Lighthouse has got our back. And they do this with an audit that they call the critical request chain. So here, running ft.com through Lighthouse, we've identified a critical request chain of 5 resources. So you can do this, even though I just asked you to do that in your head, work out what your critical resources are. You can automate this process. And if you were to take away one thing from this talk today, please let it be this, that you need to be able to be optimizing this critical request path. Eliminate every asset that is in it that is not critical to the core user experience of your website, and then optimize the remaining ones. Make them as small as possible and prioritize the delivery of those assets over the network. And that is how you will achieve a very fast time to first meaningful paint with your CSS. So if we remember the methodology for ascertaining the time to first meaningful paint, we also block on our metric waiting for web fonts, because they are delivering the user experience after all. And so look how low down in our waterfall our web font delivery is. Much, much lower than the CSS. It's around the 20th request. Now, why is this? If they're such an important critical resource, why is the browser prioritizing that network request so low compared to some of our imagery? And so to do this, we need to take a look back at how browsers go about painting again. First, the browser discovers makes the network request for the HTML document. It begins parsing that document. It finds, discovers the CSS, maybe some JavaScript if you haven't declared it as asynchronous. Then CSS can't, unlike HTML, can't be parsed incrementally, i.e. we have to wait for all of the bytes of CSS to come in before we can construct the CSS object model. And there's a very good reason for this because of the nature of the cascade in cascading style sheets, that you might have a style declaration down the bottom of your file that has overwritten something at the top. And if we were to parse it incrementally and paint incrementally, you might probably have some stuff moving around. So it's a very good reason that CSS can't be parsed incrementally. It has to wait. We then get the CSS object model, and these two trees are joined together to form the render tree. And so it's exactly like the DOM, but it only contains the elements that are going to be displayed on the screen, because you might have other elements in your DOM that you've done display none on. You've hidden them. So why does the browser need to try and compute the layout objects for those when it's not going to paint them? So the render tree is actually what is used to rasterize the page and send it. And it's only at this point, why have I even gone on this digression to tell you this? Because it's only at this point that the font files are found and the networking for them is sent. And that's because you may have a whole block, a whole paragraph of text that has a font that you've declared, but you've displayed none on that. Why should we go and perform the networking for that? Font files, by their pure nature, are very expensive. They're sometimes megabytes in size. Why should the browser perform the networking for them if we're not going to display them? And so it's for this reason that the browser doesn't perform networking for fonts until the render tree is constructed. But you'll notice here, though, we've wasted an extremely large amount of time waiting for that period. So what if we were able to hint to the browser, these are my critical resources. You're not going to find them for ages because they are a hidden sub-resource inside the render tree, but I know as the author they are extremely important. So if you imagine the 5 resources that Lighthouse identified for ft.com, they're the things that we should be hinting to the browser. And so fortunately, the Web Performance Working Group have defined a new API called Preload, which allows us as the authors of the page to indicate to the browser the critical or, say, hidden resources. So it can then prioritize the networking for them. So to put simply, it provides a declarative fetch primitive that initiates an early fetch, and this is the most important bit, separating fetch from resource execution. So I can now say, go and download this JavaScript file, but don't execute it because that will probably be bad, but perform the networking for it because it's extremely important to the delivery of my good user experience. So this is what it looks like. We now have 3 new primitives in HTML at the top via the link element with a rel preload attribute. I think this is extremely powerful. We can do it dynamically with JavaScript. So you can imagine if a user is hovering over a button to open up a carousel with images, at that point, as they hover, you can inject link preload elements to preload all of the images. So when they do click on it, you're going to have a lightning fast experience. And finally, my favorite, which is the preload link header, the often forgotten HTTP header. We can declare link elements essentially, but as headers. So here, with a HTTP header on the response of our HTML file, we're telling the browser that go and preload this CSS file is extremely important. And so going back to our experiment on ft.com, we identified those 5 resources. So we're now going to set the link preload header on the response of this HTML. And note here, there's 2 interesting points to note here, that fonts have to be declared as cross-origin, even if they're on the same origin or host, because some genius person many years ago deemed that all fonts should be treated as cross-origin for security purposes. And the important thing is the no push attribute here. I just want you to remember that for later on. So, OK, so we've applied these link headers. What impact does this have on our time to first meaningful paint? So this is our waterfall before we apply them. Remember how the fonts are so low down because they're not discovered until the render tree construction. And by applying the link headers, we've been able to tell the browser, these are my critical resources, and we've instantly shifted them up. So hopefully, you're now beginning to understand what impact this is going to have on our time to first meaningful paint. That's given us a 64% improvement on our baseline now. We've hit our budget for cable of 1,000 milliseconds, and we're very, very close now on 3G on an emerging market connection. So again, this comes with some pros and cons. It gives us a way of indicating the hidden resources. We can now dictate the priority by order. Sorry, that's a very important thing to note, is that the order of these headers also dictate their priority in which the browser will perform the networking for them. So does their relation of style and font. And the con here, though, is very easy to create contention on the network. With great power comes great responsibility. If you were just to set a preload header for every single asset on your page, you're actually not allowing the browser to do what it's very good at doing, using its preload scanner or its speculative parser to go and find and prioritize assets. So only use this technique for your critical resources that you've identified. So we could just stop there, right? We've improved our TTFMP by 64%, but surely we can do more. And this is where HTTP2's new feature called Server Push comes into play. It's now over 20 years. This is the first time in over 20 years that we have a new version of the underlying transfer protocol of the internet called HTTP2. And I could literally do a whole talk just on H2 and push in itself, but I don't have the time to do that for one, but I urge you to go and check it out. And a question I would like to ask, who is using HTTP2 in production? OK, so it's about 30% of the room from the looks of things, which is a bit lower than I was hoping, but that's still very good. So to understand, whoa, that was a bit weird. I've broken an animation. So to understand what push does, let's look at, again, how your average web page is constructed. First, we make the GET request for the index file. The server responds with the response for that index file. We parse the document. We find the link element. We go and make the request for the CSS file. And the server responds with that. But what if the server knows, as the authors of the website, we know that the next item, or resource that the client is going to request is that CSS file, because we know it has the highest priorities. So what, as an author, we could dictate to the client, I am going to push you the CSS file. You don't need to request it. And this is where the push promise frame comes in. So it's a data payload on a HTTP2 connection that the server says, I am going to send you the bytes for the CSS file. You don't need to request this. Then we can push the index file and push the CSS down. So we're eliminating the round trip completely to request that CSS file. So now we can do this with H2 programmatically, using our friend, the link preload header here. This is the semantic that we've decided upon as an industry. So now, if going back to our ft.com example, we can remove our inline CSS now, and we can declare it just as a normal style sheet, but declare the non-critical CSS as asynchronous using preload, and then tell our HTTP2 server, you have to have a H2 server enabled for this behavior to work, that I want you to push the critical CSS. And how we're doing that is just we've removed that no push directive that I told you to remember about earlier on. So a H2 server will see this response. It will say, right, the author wants me to push all of these resources, and it will push the critical CSS bytes down. So let's take a closer look at what's actually happening on the network before we apply this optimization. And note that we have idle time before we get our HTML bytes. That's when the browser has made the request, but we're waiting for the server to respond with it at the beginning. Then we have a very fast start render because we've inlined our critical CSS. Then the browser has some think time again. It then requests the main CSS file, and there's our time to first meaningful paint. Now, I don't know what you're going to think is going to happen here, but you may be a little bit surprised as the impact of pushing our critical CSS, as removing it from inline and pushing it. We've actually had a negative impact on our time to first meaningful paint. And why is this? We're not using the idle time at the beginning of the connection. And to understand why this is, we have to have a bit of better understanding of what's actually happening on the HTTP2 server here. HTTP servers use a prioritization tree to determine the order of which the packets it's going to send down the connection. And even though we told our H2 server to push the CSS via our link header, because we actually did it on the response of the HTML document, the server had all of the HTML. And HTML has a much higher priority than CSS does. So of course, it's going to flush all of the HTML bytes down the connection before it did our critical CSS, even though actually what we wanted it to do is flush the CSS in our idle time whilst we were waiting for our HTML connection. And I must stress here that this behavior is slightly different depending on your H2 server implementation, but all of the major H2 servers at the moment prioritize, and quite rightly, prioritize HTML over CSS on the connection. And so this is the impact it has on our waterfall. Now, a really interesting thing here to note is the critical CSS doesn't have a light green segment beforehand because it didn't need to send the request, and therefore there was no waiting for it. So this is the benefit that we get from push, is that we're reducing the idle time from the request to the response, but we're not getting our CSS delivered at the point that we want it to in the light blue area of our HTML. But it's also important to note, if you weren't inlining your CSS, and many of you probably aren't, this is still quite a very good technique because you are saving that request time. So we've had a negative impact on our time to first meaningful paint here of only 43% improvement on our baseline. We've gone back to 5,000 milliseconds. So the question I'm asking is, should we be using server push at all, actually, if we're having a negative impact? And most importantly, is using the link header with a rel preload actually much too late in the connection state for us to indicate the CSS that we want you to push? And so how can we actually achieve that holy grail of pushing our critical CSS only in the server idle time? And this is what at Fastly, we're calling async push. So let's look at that network utilization again from our experiment. And note, at the beginning, we have that idle time waiting for the server to respond. It's probably performing the templating, going and requesting your user data from your database. It's at this server think time that we want to be using to be pushing our static assets. And so a much more common architecture that probably many of you in the room are using is that you have your application server is actually separate from your HTTP server. I think you probably use Nginx or Apache. You might use a CDN, for instance. And so this is the request flow that the index file goes through, and then we get response. And what if that server was able, during the application think time, was able to push the critical resource at that time? This is the think time that we want to be using. So here's an example of doing that using an express-style request handler using Node's HTTP2 implementation. The important point to note here is not the implementation, but what we're doing. At the beginning of the request, the first thing we're doing is flushing our critical CSS via push down the network connection. Then we go and do our templating and fetching from our rendering. And then we respond with our link headers. And this is how we can utilize that idle connection time. And so what happens to our connection state here now is we've reached the holy grail. We've been able to push our critical CSS in the light blue area whilst the server is still thinking. We've given the browser everything it needs way before it even gets any HTML to style and paint your entire document. So now we have a 65% improvement on our baseline. We've reached that holy grail. So this comes with some pros and some cons, obviously, that we're using that idle time, but it's very easy to create contention with push. And there's limited availability of this because you have to have access to the network connection within your server to be able to do this. And hopefully, many of you are thinking, but what about the repeat view? Every one of our tests has been the first view, the uncached. The browser doesn't have anything cached, and that's what we should be optimizing for our tiny first meaningful paint. But with push, if the user was then to visit the next page on my website and I was going to push those bytes, the browser's probably got that asset cached already, but we've got no way of indicating to the server that we have that CSS, so please don't push it to me. And I did want to show you how to do this using new technologies such as service workers and the purple pattern, but unfortunately, I've ran out of time today. But the good news is, Adi Osmani is from Google, is going to be talking exactly about these types of patterns and how you can optimize for time to interactivity on your repeat view at JSConf this weekend. So let's look at the final results. And I think it's better to show you to them as how the user is perceiving this. Now with our async push example down the bottom, all the way up to the baseline, we've been able to improve the delivery on a 3G emerging market connection by over 3,000 milliseconds, which is staggering improvement for our performance. Okay, so finally, I just wanted to leave you with some glimpse of what the future is happening. We've now got a strong toolbox of APIs, Preload, HTTP push, and inlining. But there's still some issues with each of those that I outlined. The biggest weakness of server push, as we mentioned, is that via indicating that push via link preload header, is that initiation of the push is much too late in the network connection, and we end up congesting the network. And this is where my colleague Kazuo at Fastly, we now have a working draft in the IETF of the 103 early hints status code. The 100 range, a lot of people didn't even know existed. It's the information status code range. And we can now have this pattern where the client requests something from the server, and whilst the server is generating the response, it can flush an early hints response containing link headers to all of your critical sub-resources. And then the browser can go and prioritize the networking for them. And finally, the cache digest specification. Remember I mentioned that the repeat view of push, we have no way of indicating to the browser what we have in a cache for our CSS for that domain. And so now, on a H2 connection, the client is going to be able to send via a cache digest frame or a header all of the files that it has for that host name, and then the server can decide, okay, I'm not going to send you that CSS file because I know you already have it in its cache. And I think this in itself is going to be one of the most powerful performance optimizations in the future of the next 5 years as it gets implemented in browsers. So that's been a whirlwind tour. I've gone 5 minutes over my slots. I'm very sorry, my lovely CSS conference organizers. So I just wanted to leave you with some last points and takeaways. And that is that hopefully you found that resource loading in the browser is hard. It's much harder than you probably thought it was. Bandwidth is often underutilized, but we have technologies now emerging to enable us to give that utilization to the browser. Identify your critical resources and your request chains. Use preload to indicate those critical resources to the browser, especially your fonts if you're using custom web fonts. And push your critical CSS, but only in first view, and please try and only use within that idle connection time. But most importantly, always be testing. It's the most important thing to leave you with. Thank you very much.